Okay, so this is the final algorithm, and let's name it as Combined APQ. So the algorithm itself can be represented as a tree. Okay, so basically the hash family that we will be dealing with is R of and of f comma k comma tau. So we haven't said what k and tau are, but these are like, for now let's consider them as unknowns. Their values will be fixed later. A hash function h is given as input a point p computes the following matrix. And what is this matrix? This matrix is given by h of p is equal to f11 of p comma f12 of p and so on f1 f1, yeah, let's say f1k of p and f21 of p comma f22 of p f tau 1 of p comma f tau 2 of p comma f tau k of p. Sorry. So earlier our hash function was for naive APQ, the hash function just computed a single value. So in these failed approaches where we try to boost the probability, or yeah, here we try to boost the probability, or here we try to boost this probability of constant alpha, and here we try to get this number down, the number of bad collisions. So here we had like these vectors as the hash values, but now we want to combine these two ideas, and so now we have a matrix instead of just a real number or a vector. And this matrix is given by these tau times k number of hash functions, where each fij I belongs to tau and j belongs to k is uniformly randomly sampled from the original hash family capital F. Okay, alright, so this is going to be our new hash family. Okay, so now we will need a collision criterion to decide when for 2 points p comma q h of p is equal to h of q, where h is of this matrix form. Alright, so yeah, for vectors, so in this case we said that they collide if each of the coordinates, each of the hash functions f1, f2 and so on like collide. Here we Yeah, so that was here. So here we said that each of so these vectors collide if each of f1 f2 fk collide at p and q, and here we said that the collision criteria is that like one of f1 f2 and so on f tau should collide. But here we'll have a different so for this matrix kind of the hash function given by the above matrix will have a different kind of collision criterion, and that is given by this tree. So at the leaves we have these binary values 0 or 1. So given 2 points p and q, we evaluate if f11 of p is equal to f211 of q. If that's true, we put a value 1 here, otherwise we put a value 0 there. So same like we evaluate all these values. So basically we compute this matrix for like both p and q, and as you can see, so on these edges, so these are like k edges in total. So all on these edges we have this AND symbol, which means that this node will evaluate to AND of all these. So this will evaluate to 1 only if all of these evaluate to 1. In other words, and yeah, this will evaluate to, so here you have R's. So this will evaluate to 1 if at least one of these nodes evaluate to 1. Okay, so in other words, there should be one row where so you take the matrix of h of p and you take the matrix of h of q, and so for these two matrices there should be one row at which like all the values coincide. Okay, so that's when we deem h of p and q to collide with respect to the hash function h. Okay, so now we can show, okay, so we took the hash family f, and with this we created a new hash family h, right? So now we want to ensure that this new hash family h is a LSH family, but that's like easy to see given the previous arguments. So given an smaller comma capital comma alpha comma beta sensitive LSH family f, the family h given by the previous construction is a smaller comma capital R comma 1 minus alpha power k whole power tau comma 1 minus beta power k whole power tau sensitive LSH. Alright, so this should be easy. The proof is like this. So suppose distance between P and Q is less than or equal to R, then we know that probability of when F is sampled from this family capital calligraphic F of P is equal to F of Q with probability at least alpha. So when does this tree evaluate to 1? Remember that f11, f12, all these functions are sampled uniformly randomly from F. So that will happen only when at least one of these nodes evaluate to 1. So we want to compute the probability that this is 1, okay, which happens only if each of these succeed. So the probability of this, each of these is given by alpha, and there are k of these, so we have a probability of alpha par k for this to be 1. Okay, for this also the probability of 1 is given by alpha par k, and so on. For this also it's alpha par k. Now what's the probability that this is 1? So this is an R, like if one of these evaluate to 1, then we are good. So what's the probability that each of these evaluate to 0? That's given by 1 minus alpha par k. And so all of these are like with equal to 0 with probability 1 minus alpha par k whole par tau. So at least one of them is 1 with probability 1 minus alpha par k whole 1 minus alpha par k whole par tau. Okay, so that's where we get that probability of H sampled from H. H of P is equal to H of Q is at least 1 minus alpha par k whole par tau. Alright, so similarly if distance of P comma Q is greater than R, then we can show that probability of H sampled from H of Q is equal to H of P is at most 1 minus beta par k whole par tau. Alright, so this shows that the new family that we constructed, this H, is a locality sensitive hash family. Okay, so now we'll see like if the criterion that we want can be satisfied by choosing appropriate values of k and tau. Okay, so now we would like to choose k comma tau appropriately. So remember, we had two goals. The first goal was to boost the probability of a good collision. By that I mean that if distance of P comma Q is less than or equal to 1 plus epsilon times R, so the probability that we computed it to be 1 minus alpha par k whole par tau, is that the that's the expression. So we wanted to boost this probability to very close to 1, and sorry, something is wrong. So so this should be R, and if this distance between p and q is greater than 1 plus epsilon times r, then we want probability of h of p equal to h of q is this greater than or equal to this, is we got it to be less than or equal to, and we have the very crucial condition that alpha is greater than beta. So we want this to be close to 1 and we want this to be close to 0. So this makes our success probability like high, close to 1, and yeah, if this is close to 0, then it would mean that the number of bad collisions, that is if 2 points like being very distant from each other but still colliding or like mapping to the same bin, that probability, that number will be close to n times small of 1, which will be sublinear in n. That's our goal. Okay, so first let's impose the condition that one minus alpha par k whole part tau. So the success probability is at least 3/4. So this will give us that 1 minus alpha par k less than or equal to 1/4, and so this implies that alpha k times tau, or let's fix this to be 3/4, and this will exactly be equal to 1/4. And now we use the identity that 1 minus, yeah, we should use some identity that 1 minus alpha par k whole part tau is less than or equal to exponential of minus alpha par k tau. Alright, so we know this to be 1/4. So for this to hold, we say that it suffices to take tau to be 4 by alpha par k, sorry. Yeah, why is this? Like if we take this, then this will become e power minus 4, which is greater than 1/4 clearly. Alright, so we'll take this. So the first thing that we fix is tau equal to 1/4 by alpha par k. Yeah, we know alpha is something that depends on our original hash function family, but we haven't yet decided what k is. But to do that, we'll try to upper bound this to be a very small value.